Okay, and we're back. Today we're going to switch gears for the most part and segue into the last component of the course, namely inference. A little bit of administrative for this new material on inference. We're going to be focusing on chapter 9 in the main text for the book, in the main text for the. And we're back. Welcome back. Today we will be focusing on new material, and this refers to the last component of the course, namely inference. But first, a little bit on the administrative side. The focus of this last component of the class, inference, is going to be from chapter 9 for now, in the main text, probability and statistics for computer scientists. Project number 3 has been posted on the Blackboard for the course. It is due on the 2nd of April at the usual 1 second before midnight, 11:59 and 59 seconds. Okay, so where we last left off, we talked about PLA implementation, and this is the last part of it I'm going to touch on to refresh your memory. And we focused on the PLA update rule and how that manifests itself in your implementation in MATLAB. And so again, this update rule, W, the weight vector, includes that W naught, that augmentation, and the X vector, X sub I, corresponding to the ith historical record, is augmented in this case. So when you're doing the PLA update, it's important to remember that you're dealing with the augmented versions of the vectors. So it says W gets W plus XI, YI, and the XI in question has to be one of the data points that is selected. You can do it at random, and these data points have to be incorrectly classified by the current version of the hypothesis. So it says you take your incorrectly classified point, XI, the ith customer vector, and it has a ground truth label, which is either +1, -1, that's the YI, and you're going to use that to change that W. And so we have the new version of W, which is on the left-hand side of this arrow, and that new version of W is going to be the old version, so that's the old version, plus XIYI, where XI is the incorrectly classified point and YI is its ground truth label. Okay, and so let's continue forward, and we're going to talk about inference. And inference deals with first trying to find a good estimate, an estimator that you can use to stand in place for some unknown population parameter. So let's focus on this idea of what is a good replacement. So when I say the word stability, what do you think that word stability might mean? For some, it means reliable. Reliable. For others, it means you can count on it. Count on it. So others means it's there when you need it. Stability can mean many things, but when you say the word or hear the word stability, I kind of get this visual, right? Let's take, for example, the bridge. The bridge is very sturdy. All sorts of things that can happen. The wind can blow, a big truck could drive by, and so forth. But it's going to be not changing very much. It's going to be reliable, there when you need it, as you need it, and it doesn't change very much from what it should be doing. Let's take, for example, this tightrope walker. When you're walking a tightrope, well, you can be moving, but you're stable in that you're able to maintain some semblance of what your goal is, what your course or direction is. And so this idea of stability can mean it's reliable, like this tightrope walker, right? It kind of is there when you need it. It might oscillate back and forth a little bit, but it does not fall. It's firmly established, like that bridge, right? Things can come along, and over time, it does what it does and does not veer from that. And so for reliable, let's use this language. You can think of something being reliable as not likely to fail. Each time you try it again and again and again, each time you walk that tightrope, provided you're an expert, you're not likely to fail. It's also firmly established. You can count on it because it doesn't change very much, just like that bridge. And so in statistics, you can think of these tests that we used to determine if an estimator was a good replacement as determining this notion of not likely to fail, or you can count on it because it doesn't change much. And so for reliability, well, that's essentially what the test to see if an estimator is unbiased does. In the limit, as you compute it again and again and again, in expectation, I should say, it does not fail, right? It gives you this ground truth unknown parameter over time if you compute it again and again and again in expectation. Firmly established doesn't change much, right? That kind of sounds like our test for consistency. If you give it enough samples, well, it's going to get closer and closer and closer to the unknown ground truth population parameter, and it's not going to change very much. It's going to get closer and closer from what it should be. So with reliability for unbiasedness, you give your estimator, which is a function, you give it all kinds of data. You can give it outliers, you can give it typical values, and so forth. And if you measure it enough times, on average, it describes that parameter associated with the population. Likewise, firmly established for consistency, if you give it enough data, it's always very close and to the ground truth population parameter, i.e. it's a faithful description of what's going on in the population. And so let's take a refresher about what this test to see if an estimator was unbiased. Let's take a refresher as to what that was. So let's take a bunch of samples, x1 through xn. X1 and xn represent samples, and they're so-called IID, independent and identically distributed. Now, that IID assumption is really important. The independent means that one choice, so if you get sample x1, it does not influence the outcome of the next sample, or the next one, or the next one. So they're all independent, identically distributed, meaning the same population parameter that gave you the first sample is also giving you the second, the third, the fourth, and so forth. So we have this IID sample of size n, and mathematically we represent the sample as x1 for the first random variable representing the first sample, x2, second random variable representing the second sample, up through and including xn. So if we have some estimator, now we're using general terminology, if we have an estimator theta hat, where theta hat is some function over the data that we hope will stand in place for some unknown ground truth parameter, it's unbiased if in expectation E of that theta hat, we get exactly theta, the unknown population parameter. And so let's assume an example. That means if theta hat is s squared, the sample variance, we hope that it would be a good estimator for sigma squared, which is the population variance. In expectation, you can prove by direct proof that the expectation of s squared, or sample variance, computed over the samples, x1 through xn, is exactly sigma squared, and you can do that by direct proof. Okay, if theta hat is, for example, a different estimator, x bar, which is the sample mean, is computed over samples, x1, x2, x3, up through and including xn. If x bar, the sample mean, if it's an estimator for mu, the unknown population mean, that means the expectation of x bar is equal to mu. And you can absolutely also prove that by direct proof. Okay. So let's turn our attention to consistency. Again, we have an IID sample, x1, x2, x3, up to and including xn. And what consistency says, to jar your memories, that given an estimator, theta hat, in the limit, as you increase the sample size, so here's our sample size, little n, as it goes to infinity, in the limit for this estimator, theta hat, if the probability that the magnitude of theta hat diverges from this theta, the ground truth parameter, is no more than some error epsilon, that's going to go to zero, that probability. So that means as you get more and more samples, it becomes less and less likely that your estimator is going to be different from your ground truth parameter. Okay, so let's consider for S squared, the sample variance, as an estimator. For sigma squared, the population variance. So by consistency, how we would show that is if we can show that this estimator, so this estimator here, our theta hat, we're considering theta hat as being S squared, if that theta hat in the limit at the n goes to infinity is exactly equal to sigma squared, that means this probability is going to go exactly to 0. Why? In the limit, as n goes to infinity, our S squared is going to equal sigma squared. So how does that affect our probability? Well, if S squared in the limit is exactly equal to theta, right, that means that it won't diverge. If it's exactly equal, it can't diverge, and so this probability is exactly 0. It's satisfied. So one of the ways you could prove that S squared is consistent is by taking the limit as n goes to infinity and showing that it's exactly equal to theta, to sigma squared. So let's also turn our attention to the consistency for x bar, the sample mean. X bar, if it's an estimator, a good estimator for the unknown population mean, mu, that means one way to prove it, again, in similar fashion, is to take the limit as n goes to infinity of our x bar, and if you can show that it is exactly mu, well, mu is no different from mu, and so the probability that it exceeds the population mean mu by more than some epsilon is always going to be 0 if it's precisely equal. Okay? All right. So let's take a look more generally at what is inference. Now, in inference, recall when we had the example for the homeless population, we talked about having a group of people about whom you can't really know ground truth what certain governing attributes are. And so we had partitioned our population into 4 subgroups that are non-overlapping. That's a simplification, I acknowledge that, but this for the sake of discussion. Nonetheless, we have a population consisting of 4 subgroups that are non-overlapping. We had the homeless veterans, we had the homeless families, those who are drug addicted, and the aged out foster kids. Now, of course, we took samples from them, and these subgroups were governed by ground truth parameters, theta 1, theta 2, theta 3, and theta 4, as we depict here. Now, of course, these population parameters, we don't know what they are, but what we're going to do is compute some function over a sample, a statistic, and use these estimators as replacements for these unknown quantities. So, for example, we'd sample some veterans, then we compute a statistic, and that estimator we're going to call theta 1 hat. Now, of course, the hatted version corresponds to the estimator for the ground truth population parameter, which is the unhatted version. So we have theta 1 hat, which is going to stand in place by computing an estimator. It's going to stand in place of theta 1 by computing an estimator over the homeless veterans. Likewise, we do similarly for the families, for the drug addicted, and the aged out foster kids. Okay, so if these estimators are stable, going back to our definition of stability, that means that they are reasonable replacements for these unknown ground truth population parameters. So if they're stable, that means they're reasonable replacements. And remember that we want, or we're enterprising to be able to make statements about the general population based on some summary information. And so this is done for a whole host of reasons, because it saves time, saves money, saves effort, but also there are many cases, such as finding members of the homeless population for your town or city or area. You'll never be able to find all of them, right? It's virtually impossible. So instead of dealing with the actual population, now you're dealing with the estimators that are good replacements for the governing population parameters describing your population. Okay. So every statement we make, the hope is, every statement that we make about the population from these replacements, these estimators, theta 1 hat, theta 2 hat, theta 3 hat, and theta 4 hat, we hope that it would apply, and it does, it would apply well to the original population. Now that's pretty amazing. You don't know something that's out here, and by choosing a function, theta 1 hat, if you choose it the right way, theta 2 hat, theta 3 hat, and theta 4 hat, well, you don't know everything about this whole population, but yet there's something you can do to understand that population even though you don't have complete information. Now, I remember when I first learned this, I was like, wow, this is pretty amazing. It is amazing. So now we're going to deal with these estimators, these summaries, and every statement, if these are good replacements that we make, every statement that we make about the population based on these replacements, it will apply very well to those original population members, not all of whom you know who they are. So let's give a framing example. And in this example, suppose we want to deal with customers arriving at a store. So imagine, if you will, if you go to Starbucks, so if you go to Wawa's down the street from campus, do you know about how many customers come to the store every minute of the day, every 5 minutes of the day, and so forth? Do you have any idea? I don't. It's not a trick question. But suppose you're dealing with this issue of the number of customers that are arriving at some store. Now, of course, an employer would love to know this because you want to make sure that you're hiring enough employees, or you have enough employee staff for certain times of the day to serve the customers well. So this is an example of a measurement that someone has set up for a store. Let me see if I can get the pen back. Here we go. This is a setup of a sensor system overhead for the entry box in a store. And it tracks the number, not the identity, but the number of people that enter a store and leave a store. And you can see these green boxes that are scribed around the tracked subjects, the blobs. And we'll go to full screen with this. And it tracks the blobs as they go from outside of the store through the entry box to the inside, and likewise from the inside to the outside. Now again, it's just tracking heads through the entry box, but it has no concept of identity. Another thing I'll draw your attention to is it has a tally. The total number of people who've entered the store, so there's 1179, that's 1180, 81, 82, 83, and the number of people who've left the store. The difference between the number who've entered and the number who've left, of course, are the number of people who are inside the store. So with this, for every, say, 1 minute block of time, or every 5 minute block of time you pick, you can actually calculate how many people are in the store. And you also have information about how much revenue you're collecting at the register at each period of time. So you can literally track the arrival rate of customers and use that to calculate roughly how many employees you should have during certain times of the day. Okay, so from last semester, when we talked about the Poisson distribution traffics in events that arrive in time. And we said with the Poisson distribution that you have windows of observation, delta t, and delta t could be minutes, could be 5 minutes, could be 15 minutes each, and the only prerequisite that the delta t's have to be the same. We have to be consistent. And then we talked about a rate, R, as being the average number of observations in each one of these windows. So we know on average how many events occur within those standard delta t units of time over time continuously. So this is modeled by the Poisson distribution. X, our measurement, is distributed as, and X stands for the number of occurrences of an event. X is distributed as a Poisson and is governed by parameter lambda, where lambda is the so-called rate parameter. And so this is a probability mass function because this is a discrete distribution, because numbers of events is countably infinite. And the mass function, p of x, the probability of observing some number of occurrences x of an event, is e to the minus lambda, lambda to the x upon x factorial. And so when we did the calculation of the mean and the expectation last semester of a Poisson distributed random variable, the Poisson was a little bit unique in that its mean and variance, mu and sigma squared, was both lambda. So we have the mean is lambda, and the variance is lambda as well. So now, given a system like we had in the previous slide, you have actual counts of number of people or customers coming into a store. So if you know that the sample mean is a stable estimator for the population mean, and we've proven that throughout the course of the semester, we know that the expectation of x bar is equal to mu. So what does that mean? It means that now you can replace everywhere you see that population mean, you can replace it with x bar. And so for the Poisson, we know that the population mean of Poisson is lambda. So that means everywhere we see a lambda, if x bar is a good replacement for the population mean, lambda, we know that everywhere we see lambda, we can replace it with an x bar. So here in our expression for the probability mass function, we have e to the minus lambda, so we can replace that with an x bar. We have lambda to the x power. We can replace lambda with the x bar. So we do that, and now we get the following expression. E to the minus x bar, and remember x bar is a quantity. You get some samples, measurements, like you would get from that camera system, counting customers coming into a store, and you compute x bar from those numbers of people that arrive over units of time, and then you take that x bar and you use it as a replacement, that value you calculate, use it as a replacement for lambda. So now you actually have a real Poisson distribution. And you'll note that x bar is measured from the observations. It is a constant value. Let's say 10 customers come in and then 20 customers come in. X bar over those two observations would be 10 plus 20 divided by 2. That would be 15, right? So your x bar is an actual value. Okay, so now given this Poisson that has known values filled in for lambda, you can now sample from it and ask all sorts of questions. So what would you do? In something like MATLAB, you would produce a bunch of samples, and now you can ask all sorts of questions. Here are some example questions. Is it typical for 20 customers to walk into the store, right? You just evaluate P of 20 given these x bars, and then if that probability is very small, you'd say no, it's not typical. If that probability is large, you say yes, it is typical. How much revenue can I expect to collect? Okay, well, if you know the average dollar amount, you multiply that average dollar amount by the expectation of this particular Poisson. Or, similarly, you could simulate by sampling the number of events or customers that walk into the store from this particular Poisson distribution for which you've made the substitution, and then multiply each customer by the number of dollars on average each customer spends. And that can be your forecast, your educated guess, if you will, about how much revenue you can expect to collect. How many employees can I afford? Okay, well, you know how much you've sold, you know what your margins are, the difference between what it costs you and what you sold it, and then you say, okay, well, given my other expenses, can I afford to pay these employees? Because you know their hourly wage and you know their salaries. So you can ask all sorts of questions using this simulation just by instrumentation and using those good replacements, our estimators, and then sampling from the resulting distribution. Okay? All right. So let's take a look at an approach. We said before, if estimators are stable, they're reasonable replacements for some unknown population parameter, but we have no idea what these population parameters are. So we deal with these estimators instead of dealing with the entire population. And so a method that's going to help us is something called method of moments. So mom to the rescue, method of moments estimation. And it's a scheme for producing so-called good estimators, finding these good substitutes. And the approach used by method of moments is to equate two things, to equate an unknown with a known and then solve. Now that unknown is the population moment, and the known is the sample moment, something that you can solve or compute from the data. And we'll get into what that means. But before we do so, we should take some time to explain what is a moment, because we haven't defined what a moment is. So this is probably going to get pulled down. I always believe that you can find a song to represent just about every concept. For those of you who are too young, this is a record player. It's almost like an analog version of a DVD. You won't have tears in your eyes when you're calculating statistical moments. But nonetheless, what is a moment? Now, of course, when this was being developed by the statistics community, there are already perfectly good existing tools out there, so they made use of those tools. Now, the definition of a moment, this is from physics, it's a combination of a physical quantity and a distance. And so here's a wrench, and we have some nut, and you want to apply some force, and using a moment, a lever arm at some distance, you can effectively multiply the force that you can apply. And the moment is, the definition of it is a force at some distance. And so here in this example, we have a hand, an arm, and you're pushing with a certain force downward direction. And this force is 50 newtons magnitude. And this wrench, the lever arm of this wrench, is 0.1 meters. Now, of course, here at this pivot, you're going to multiply your pushing force proportional to this distance at which the force is applied. And let's make the assumption that the material is strong enough that it's not going to bend. And so effectively, you're multiplying this force by that distance. If the distance is shorter, the force is less. If the distance is longer, the force is going to be more, as seen at that pivot point. So why do we care about this? Because, hey, wholeness, we're talking about statistics here. Why do we care about these moments? So why did I have that there? Okay. So why do we care about these moments? Well, let's look at this seesaw example. We have two weights, and the seesaw is about a balance point that we put in the center. And 1 meter away from this balance point, we have a weight that, when subjected to acceleration due to gravity, it's going to exert 20 newtons of force in the downward direction. On the other side, 2 meters away, we have a weight that's half as big, and it's going to exert 10 newtons of force in the downward direction. Now, it just so happens that the smaller weight, literally half the size or half the mass, is at twice the distance. And so perceived at the pivot point, what's going to happen here? We're pushing at 20 newton meters, at 20 times 20 newtons force at 1 meter, so it's 20 newton meters, and it wants to turn this pivot in the downward direction. And it wants to turn, let me get the pen, and it wants to turn this pivot in the clockwise direction. Now, let's consider this smaller weight that's half the weight. It's 10 newtons of force in the downward direction at a distance of 2 meters. It wants to pivot this seesaw in the other direction. And so here we have 10 newtons times 2 meters. That's 20 newton meters. So we have 20 newton meters that wants to push in the counterclockwise or anti-clockwise direction. And then we have 20 newtons times 1 meter, 20 newton meters that wants to push the seesaw in the clockwise direction. So 20 Newton, it's equal in opposite directions, so it's going to balance. And so that's the point here, is that it balances, but more importantly, this weight on the left-hand side of the seesaw is only half as much weight. So with half as much weight, we can exert the same amount of force just by bringing it a further distance away. And this distance is effectively multiplying the force on your behalf. So let's take a look at this video. And it's a discussion, a pretty good one, about moments in general.
All right, Desmond here again. I want you to look at something else and see if you can explain how it works. Okay.
Okay.
Falls over. Someone's going to have to give us an hand. Only those short hands. Hey, look at that. How's it still? Hey, shut it over there. Oh, sorry. Desmond Jr. Getting a bit out of order. Anyway, when a piece of wood rests on the desk, the bottom bit acts like a pivot. The weight of the wood, which is caused by a force of gravity, acts as if it comes from one point, which we call the centre of mass. Now obviously the mass isn't really just in one point. The wood, it's spread throughout the wood. It just behaves as if it comes from one point. So, we have a force acting at a certain distance from the pivot. And this creates a turning effect. We call it a moment. That's why the wood falls over. Now, when the bottle of wine is placed in the hole, the centre of mass of the object changes. So now it's above the base. So it's stable and it doesn't fall over. Another way of looking at this is that the weight on either side of the pivot is the same. So the object is balanced. The clockwise and anti-clockwise moments are the same. That's why it balances. Okay. Shut up!
All right. So it's a little bit kooky, but it gets the point across. And so in statistics, a moment generally measures the shape of a set of points in a distribution. And so here we have a number of data points. Along the horizontal axis, we have their values. Along the vertical axis, we have the probability associated with those points. Now, you can think of a probability as referring to a mass of a certain size. Now, as a mass, gravity acts on each mass, exerting a force in the downward direction. So if, for example, x3, it has a larger mass, therefore the force is going to be larger, and we connote that here as just the magnitude of that arrow from point x3 because its probability mass is higher. So you think of a probability as a mass, and as masses, gravity acts on them with a force, and that's the weight that you experience. Okay, so more mass means bigger force, and we draw that in as depicted with a longer arrow. And let's select a pivot point. And this pivot point, by the way, what point is this? This looks a lot like the median, right? It could also be the mean, but it's a central point. So we can actually compute a value by adding up the moments, which is the forces times the distances that each of these mass points, probability mass points, exert relative to the pivot point, force at a distance. And so if you do that, you can also select a different pivot point. And this different pivot point is where all of the moments sum to zero. If you select a pivot point where all of the moments sum to zero, that is the plank, or if you imagine this axis as a board or a seesaw, it's going to balance, right? And so there's another pivot corresponding to the balance point, and the balance point is that location along the horizontal axis, where if you place the pivot, everything's going to balance, and it balances because the sum of the moments is going to sum to zero. So the balance achieving a pivot has a special name. It's called the mean, or sometimes it's called the center of mass, because the center of mass is that place where something will balance. Okay, so the mean is where you have center of mass, or the point where the sum of the moments of each one of these probability mass points is going to balance. It sums to zero. So let's get back to values that we can compute by adding up the moments. So you take your values, you sum them together, in this case for each of the 8 data points. Now, if you sum together these values reference or relative to zero, right, their differences between their location and zero, that's the distance. And there's a problem if you sum together these moments, right? If you sum them together. Well, the problem is that if you shift things by adding the same value to each one, well, you're going to get a bigger sum. The same shape distribution then will give you a different result just by shifting it, and that's not a good thing. So you fix this by shifting the distribution so that its center is aligned with the origin. So how do you do that? Well, you subtract off the sample mean. If you subtract off the sample mean, the mean is the center of mass, you subtract that off from every element, every data point, every mass point, and now you have a consistent way of evaluating the shape of a distribution. So you subtract off the mean, it's called centering your distribution. And more generally, we talk about moments as being the sum of the forces times their distance. So what does that look like? Well, we can generalize moments into the so-called nth moment. And here we're using an integral, but if it's a discrete distribution, we use summation. So the nth moment, mu sub n, is equal to x minus its center, and you take that as a quantity and exponentiate it to the nth power. So that is the distance, and now the force is the probability f of c, right? All right, so here we have the sum, which is encapsulated in this integral. We have distance from the pivot point, difference from the center. We raise that to the nth power for the nth moment, and then we multiply that times the force. Now that shouldn't be f of c, it should be f of x, right? Because you're talking about the force, i.e. the probability of that mass point x. Okay. And so this is the general expression for the nth moment. And just for good measure, I will correct this. It should be f of x. Here we go, f of x. All right. So this is our general equation for the so-called nth moment. It's centered at origin, so C, or the center, is the mean mu. It's also centered at the balance point if C is equal to 0. Okay, so the first moment is called the mean, right? The mean is the first moment and it's not centered. You're not subtracting off the center when you compute the mean. The second moment, centered about origin, that's the variance, right? So the moment is the general framework you use for talking about the shape of a distribution. That second moment talks about how dispersed or spread out the distribution is. First moment talks about the location, this balance point of your distribution, the center of mass. So one talks about location. A second moment, that's centered, you subtract off origin, that is how dispersed it is. The third moment, centered about origin, is the so-called skew, and this measures how lopsided your distribution is. And then the fourth moment talks about kurtosis. This is the measure of flatness. And so this all fits into the moments framework, where the second moment, third moment, and fourth moment centered about origin is the variance, skew, and kurtosis, whereas the first non-centered moment you know and love as the mean. Okay, so let's take a look at the third moment centered about origin, right? That's the skew. That talks about how lopsided the distribution is. So let's take a look at this. So here we have an example from the physics domain. We have a seesaw and we have a pivot point, and relative to that pivot point we have a mass of 20 newtons, and we have a mass at 1 meter, and we have a mass of 10 newtons at 2 meters. And so if we add them up, right, we have -2, which is the distance of this smaller mass on the left, -2, because it's in the negative direction from this pivot, -2, we cube that, minus the center, it's called the center origin, cubed times 10, all right? And then we have 1 cubed times 20. So if we add them up, that gives us exactly 8, -8 times 10, that's -80, plus 1 times 20, that's 20, so it's going to be -60, right? So in terms of skew, this is more lopsided on the left-hand side, the negative side, which is exactly correct. So if we take a look at another example, let's now put 10 newtons at 1 meter away, right? So here's 10 newtons at 1 meter away from the balance point, the center, and here's 10 newtons at 2 meters away. So let's take a look at this skewness. All right, so we have at -2 distance 10 newtons, and we have at +1 distance we have 10 newtons. So if we do this, okay, so that's -2 cubed times 10, 1 cubed times 10. So what does that give us? That gives us 2 cubed is 8, so that's -8 times 10, that's -80, plus 10, that's 70. So it's going to be lopsided. So let's take a look at this other example where we have two 10 Newton forces, each equidistant from the center, 1 meter away. So that's -1 cubed, that's -1 times 10, that's -10, minus +1 cubed, that's 1, times 10, that's 10, minus 10 plus 10 is 0, and guess what? This balances. So in the previous case, because it skews negative, it's going to tend to tip to the left. Left-hand side is going to be closer. In the other case, it's going to tend to tip to the left as well, to the left side. And so here, the skewness tells us about lopsidedness, and the physics coincides perfectly with the statistics. Okay, so let's take a look at our method of moments, and this is a recipe, if you will, for using moments to determine what is a good replacement for an estimator. So we talked about moments previously. We talked about what a moment is, motivated by the physics, and we also talked about some examples relating the general form of a moment to our treatment in statistics, and looked at the median versus the mean and how it describes the shape of a distribution. So notationally, we would write the kth population moment. Now remember, this is a theoretical construct. Mu sub k is equal to the expectation of that random variable raised to the k power. So mu sub k is a population moment. This is what it looks like for discrete distribution. We have the sum of each measurement xi to the k power times the probability of that xi to the kth power. Okay, probability of x. Now the kth sample moment is as follows. The sample moment is just 1 over n, right? You're treating each sample as being equiprobable, and so that would be the sum, I goes from 1 to n, of xi to the k times 1 upon n. Now there's a little bit of a typo here. This typo, that should not be to the k. It should be the sum I xi to the k power times the probability of xi, right? That shouldn't be xi to the k power inside of the probability. Okay, so we have the population moment, the kth population moment, and we have the kth sample moment. So estimates, the sample moment, we estimate mu sub k with the sample moment. We can make estimates mu sub k from a sample. So the first sample moment is the sample mean, right? That's what the first sample moment is, because if k equals 1, we get exactly the sum. I goes from 1 to n of all the xi's, and we multiply by 1 over n. That's the same as dividing by n. And so we're going to produce estimates for mu sub k, the population moments, using the sample itself. And the first sample moment, just plugging in for that k equals to 1, that would be m subscript 1, is nothing more than the sample mean. So let's look at central moments. For k greater than 2, we'll talk about the population central moment, meaning it's the population moment, but we centered it by subtracting off the mean. So here, mu sub k, if we substitute k equals 2 or k greater than 2, is the expectation of x minus mu sub 1, the first population moment, or the population mean, raised to the k power, because this mu sub 1 is the center or the balance point of a population distribution. So this mu sub k, where k can equal 1, k can equal 2, and so forth, is just the expectation of each measurement minus the center, mu sub 1, all raised to the k power. So you take this quantity, raise it to the k power, and then you take the expectation. Okay, and that's mu sub k. And so if we write this out longhand for discrete distribution, this is equal to the sum of each xi measurement minus mu raised to the k power times the probability of xi. This is our kth population mean. We also have the kth, this is the kth kth population central moment. Now, the kth sample central moment, we centralize it. To centralize means you subtract off the mean. Now, we call that M prime subscript K. That M prime means it's the population central moment, right? It's the kth moment. So that's just the sum of each measurement xi minus the population mean. So here you minus the sample mean. Here you're using the sample mean, right? That's really, really important. Here you're using the population mean as the center. Here you're using the sample mean as the center. This is the sample central moment, and it's centralized, so you're subtracting off this sample center, which is x bar. Okay, so we have M prime sub k is 1 over the sum of the difference, that distance between each data point and the center, using the sample version, all raised to the k power. So if you're talking about the second sample central moment, that k would be 2, and this would be a square. And that looks a lot like the sample variance. Okay, so the idea then is that you're going to compute an estimator for mu sub k, and you're going to do that from the sample. And so if we look at the second central moment, that's the variance. Here's our equation for the variance, is the expectation. So we sum xi minus mu1 quantity squared times p of xi. And the sample second central moment, so we have two versions of the second central moment. We have the population version and we have the sample version. Here's the sample version. So s squared, as we know it, is m2 prime is 1 upon n, the sum of each of the xi minus the sample mean quantity squared. So that's the sample version of the second central moment. It's central because you're subtracting off the center, and it's sample because you're using the sample mean, and this is the sample version. Okay, so we have two different types of moments. One is the population moment, and the other is the sample moment. So one of the questions that is there, and you probably realize this already, why do we have this leading coefficient 1 over n? And not 1 over n minus 1. So pause and think about that. Okay, why is the leading coefficient 1 over n and not 1 over n minus 1? It's biased, right? So this version, this sample second central moment, is biased. To make it unbiased, you have to rescale it so that we get that coefficient 1 over n minus 1. It's not the unbiased version, it's the biased version. Okay. And so what does method of moments estimation do? It follows the simple idea that in order to find a good replacement for an unknown population moment, you just equate it, the formula for that unknown population moment, you just equate it with the sample version and then solve for the unknown. So there are many distribution families that we've studied. We've studied the Bernoulli, the binomial, uniform, Poisson, exponential, gamma, negative binomial, the normal or Gaussian, etc. All sorts of distributions. And so you want to know sometimes which one we should use. Each family, as we found last semester, has a set of parameters, and these parameters, we'll just call them theta, govern the behavior of each distribution. So for example, if we're talking about the Gaussian or normal distribution, it has two parameters, the mean and the variance. And the bigger the mean, the more to the right your Gaussian distribution shifts. The smaller the mean, the more to the left it shifts. The bigger the variance, therefore the bigger the standard deviation, the more dispersed it is. The smaller the variance, the smaller the standard deviation, and the less dispersed it is. And so we have these parameters for each one of these distributions. For example, the Poisson has a parameter lambda. If lambda is bigger, the rate in each window of observation delta t is higher. If lambda is smaller, the rate is smaller. And so each family of distributions has a set of parameters that govern the behavior, where here we're talking about behavior as referring to the values we will see. So when we're solving a problem, we choose the distribution family whose properties most closely match the properties of the data. And these properties are described as moments, because how you distinguish one distribution from another is one way is by its shape. And you use moments to characterize and describe its shape. Okay, so what do? Let's go back to this customer arrival problem that we watched for the video counting the customers. You observe the number of events occurring during some number of windows of observation n. Now n goes to infinity. This delta t, the only requirement for the Poisson configuration is that these delta t's had to be the same. So what do? You take the first population moment, mu1, defined by the equation we had for moments, and you equate that to m1, the first sample moment, m1. And so what is that? Okay, well, what is mu1? Mu1 is e of x. That's the expectation of x to the kth power, where k is 1, because we're talking about the kth moment, the first moment. So we have e of x, and we equate that with x bar, where x bar is the first sample moment. So once we do that, okay, what do we get for the Poisson? So what is the expectation of a Poisson? It's lambda. We equate that lambda with x bar, and then guess what? We know that we can replace this lambda with x bar. And so one bit of caveat to pay attention here. We know that the expectation of x for Poisson is lambda, and we say lambda equals x bar. So now you know that x bar is the replacement for lambda. You write this hat over it to connote that this is an estimator, because we're doing method of moments estimation. We're computing a statistic from the sample version of the moments, and we're using that as a replacement. So if we're going to use it as a replacement notationally, you need to tell your audience that, yes, this is a replacement. So we then take this result that we just computed, and we put hat over the population quantity to connote the fact that this is a substitute for lambda. So a substitute for lambda is called lambda hat. Lambda is the population parameter. The substitute for lambda is called lambda hat. And this is called the method of moments estimator for lambda, this lambda hat. So what does this mean? It means that if we want to replace from observations this unknown population parameter, we can do that with x bar, and it's going to be a good replacement. Okay? All right. So that's all I had, and we will end there. And again, please make sure you start reading through chapter 9 and that you're already underway in starting project 3. I will see you on Tuesday.